let's do problem 15 on page 98. And I'll go ahead and read the problem. It's right here. It says, a person stands on a bathroom scale in a motionless elevator. When the elevator begins to move, the scale briefly reads only 0.75 of the person's regular weight. So when you're looking at the bathroom scale, it only reads 3/4 of your weight. Calculate the acceleration of the elevator and find the direction of the acceleration. Okay, so I've already set it up here with given, find, and solve. Okay, we got somebody in an elevator. The force that the scale reads is 0.75 grams. Now, one of the things that they talked about, and I talked about, is that bathroom scales don't measure your weight. They measure the force of that interaction force between your feet and the scale. So now, here's what I recommend you do. If you have a bathroom scale at home, especially the old-fashioned kind that are not electronic, it won't work with an electronic scale, but with the one of those spring-based bathroom scales, stand on the bathroom scale and look at your weight. You know, you'll see the reading of your weight. Start flapping your arms. And you will notice that your weight gets greater and lesser and greater and lesser and greater and lesser. Now, if you do this in front of a full-length mirror, you will notice that you are not getting fatter and skinnier and fatter and skinnier and fatter and skinnier. So what's going on? Well, when you push your arms down, you're accelerating mass down, the mass of your arms down, and so you're going to read lighter. Then when you have to stop your arms at the bottom, you have to apply a force up on your arms, distributed through your body into your feet, into the bathroom scale, and you're going to read a little bit heavier than your weight. If none of your mass in your body is accelerating at all, then the force of the spring of the scale up has to be equal to your weight down, and so you are getting your actual weight. So because this spring scale does not read something that's equal to your weight, oh, and I miss, this should be times the force of gravity. It's 0.75 times the force of gravity. All right, so let's do this. What I'm going to do is just draw a picture of the person, but I'm going to draw the person as a dot because it took me a long time to draw that. All right, so what forces are acting on this person? Well, Earth is pulling down with the force of gravity. And this is the force measured by the scale. Now, you can call it a normal force. Spring scales measure the normal force between your feet and the scale. So if you called this the normal force, that is perfectly fine with me. Just make sure you know that bathroom scales measure normal force. Now, I also know that when I add up all the forces, I get the net force. And the net force is equal to the mass of the person times the acceleration. Right? Now, an impatient student would give up right now because they would say, well, I don't know the mass. They didn't give me the mass. I quit. Be patient, Potty 1 learner. Okay, you will. It might show up. You might be able to solve it even though you don't know the mass. And this tells me what to do. Add up all the forces. Well, I'm going to say that up is positive. This is positive y. So I'm going to add these forces. This is the force that's on the scale minus the force of gravity equals ma. Okay. Now this is good because this has acceleration in it. That's what I'm trying to find. Then I'm going to look at the force on the scale. The force on the scale is given to be 0.75 times the force of gravity minus the force of gravity equals ma. Well, what is the force of gravity? right? The force of gravity is equal to, just like what we did in the lab, the force of gravity is the mass of the person times the gravitational field, G. Now remember, this G right here is a subscript. This G right here is a number that we multiply by. It's the gravitational field strength. It's how much force gravity gives per kilogram of mass. So this is 0.75 times the mass times gravity minus mass times gravity equals mass times acceleration. Well, this is awesome because look, mass is in every term. So divide both sides by the mass, and it cancels out. The only time you can cancel out something is if it's in every single term in that equation. So we have 0.75, and we know what gravity is, right? It's 9.8 meters per second squared minus gravity, 9.8 meters per second squared equals A. And so when I get my calculator out, I mean, you could have distributed or factored out and make it a little bit easier, but I didn't. So 0.75 times 9.8 equals 7.35 minus 9.8 gives me an answer of negative 2.45 meters per second squared. But it's negative. What does the negative mean? That's the direction. It's down. So rather than put the negative there, I'll just say down. We're accelerating 2.45 meters per second squared in a downward direction. And if you want to leave the negative in there, that's fine, as long as, because I defined up to be positive over here. So next time you're on an elevator, notice this. When the elevator starts accelerating down, you feel lighter, don't you? Oh. Do you jump? Do you jump? I jump. I still jump. I'm an old man and I still jump. All right. Because you're accelerating down, so you feel lighter. Now, what if the elevator wasn't accelerating at 2.45 meters per second squared down? What if it was accelerating at 9.8 meters per second squared down? That would be awesome. You would be in free fall. You would float around in that elevator like an astronaut in space. It's probably an experience that won't last very long and could very well be the last experience you ever have, but it would be awesome. That is all.